stuff. Yeah, right. So all these things have a reason. We're talking about thermodynamics and energy. We've made the case that what it does for us now is in two things. It changes our Bernoulli equation so that there are head losses and head inputs, energy inputs and energy losses in the system. And I made the case that, say, for flow in pipes and flow in porous media, which is what this is, flows, the essence of the flow is the drag that's placed on the flowing water by the viscosity of the fluid as it flows past the grains. So in this little plot, you see individual rounded grains, a porous medium. You see fluid blobs squeezing between it for perhaps water and gas flowing downstream between the left-hand side and the right-hand side. I think the color scheme is for high pressure red to low pressure blue. And it's actually an advertisement for a company called Ingrain, who were bought out by Halliburton not so long ago, who a colleague of mine here went from here to be I think he was the chief technology officer for it. And the idea is quite simple. You drill a hole into gas shales, say. The drilling brings up chips, size of your thumbnail, small finger thumbnail, small finger fingernail. And from those chips, you can CAT scan them, X-ray CT them, so you can exactly get a map of the porosity of that chip. And then you can run a model that basically takes a lattice of individual points that allows you to solve for flow within it. So this is just an animation of a numerical model of a porosity map, the porosity represented accurately, and to look at the magnitudes of fluid flow rates through that. And so one thing that you could do would be to look at applying a pressure upstream, a pressure downstream, measuring the amount of fluid that comes out of the bottom, and defining that as what we'd call Darcy's law. If you've seen it in any of your courses, you certainly will in almost all of your majors, to understand exactly what the physical properties are. And Darcy's law is an empirical law that says if you double the pressure differential between upstream and downstream, you double the flow rate coming out of your cube. And so it's a linear relationship. Or if you change the viscosity, if you double the viscosity, you halve the flow rate. So it's related to a hydraulic conductivity or permeability and a viscosity. And it allows you to account for the frictional losses in the system, even though you're only using mass balance equations. And we may look at those later on today if we get to it. So that's one thing to look at. More impressive than that, though, I think, are these videos. And these are also simulations, but in the same way that in the pore space, actually we're solving the momentum equation with fluid losses for viscosity. And so it's actually, even though Darcy's law is a different thing and doesn't really matter now, it's too complicated to worry about. This is solving the linear momentum equations by a method called SPH. Okay, I don't want to do that quickly, get there. No, I don't want to do that. I want to go back. Can I do that? If you go here, that's the wrong one. If I go back, does it go to the right place? Yeah, okay. Smooth particle hydrodynamics was the name I was working for, SPH. And what it does is it treats each block of fluid as a particle that's flowing through the system. So you can imagine this as being a hose that's squirting out a whole bunch of marbles. But those marbles, instead of being glass, happen to be fluid. And when they meet other marbles, they coalesce in some way and become this fluid at the bottom. And so it's just a technique that's using the idea of representing the fluid as a bunch of individual particles. I think this is the same kind of idea. Whole bunch of particles filling up a box which you can't see, but is rendered somehow so that it comes up against the wall. Is it over that quickly? See if it does the same. And the same idea. Each packet of fluid is represented as a packet of fluid that interacts with those around it. If it doesn't attach to one of the particles around it, then it just keeps on going. I want to make sure that's stopped. Don't want this going in the background. And I can't remember what this is. This is a whole bunch of animations. Yeah, okay. And the same kind of idea. And so you represent fluids in some way as individual particles, and you solve it on a lattice in some way. And you can also represent solids that are just particles that don't deform in some way, right? That have some buoyancy. So the things we're doing, we won't do anything this sophisticated in this class, but this is ultimately where the things that we've talked about, conservation of mass, conservation of momentum, are embedded in these equations, because these equations are really just solving F equals ma. And you could think of dropping a weight, and the rate at which it will accelerate is given by F equals ma. You can calculate exactly how it would accelerate based on your knowledge of dynamics. And all this is doing that, instead of looking at a single particle, it's maybe mapping them as it goes through some kind of lattice. So you could think of either following individual particles and allowing that particle to be represented by F equals ma. If it hits another particle, you look at the contact between them and trying to evaluate what the exchange of momentum is between them, whether they would coalesce, if they're solid, whether they'd bounce off each other. Or alternatively, you could look at the behavior on a static grid, which is this right-hand side is showing, and you can look at the fluid coming in from the right-hand side of that grid, coming out of the left-hand side of that grid. There's a mass balance there clearly, and also there's a momentum balance that you could track. And so these are relatively sophisticated calculations, as you can imagine. They're much more difficult when you have a free surface involved, because you don't have a closed boundary to your system. And you can see on the bottom left-hand inset that the mesh kind of grows as the free surface grows, to be able to accommodate the fact that you have little beads of water breaking off that have to be accounted for in the overall mass balance equation, right? And so you could imagine that even in this big grid, the flow in from the left-hand side has to equal the flow out of the right-hand side, and the difference between those would be accumulation in the volume that's in between those two left and right boundaries. You can apply that to the overall system, but you could also apply that to the individual grid boxes, that flow in equals flow out, and if they're imbalanced, then there's some accumulation in that individual box. And so that's how these numerical methods work. They're a bit complicated to explain, but that's the basic principle. And you use conservation of mass, you use conservation of momentum. And for these kinds of solutions, which would be called Navier-Stokes solutions, after George Stokes, and I don't know what Navier's first name is, a famous French mathematician, you end up with a system of equations where you want to solve for velocities in x, y, and z, and the pressure at each grid point in our system. So there are four variables that you could imagine you have to solve for. The flow rate of the velocity at x, in y, and z, and whatever the pressure is. And so you could imagine that to solve for that, if you have four unknowns, you need four equations. And the four equations you need, I think this is the neatest one. The four equations you need are conservation of mass, one equation, conservation of momentum in x, in y, and in z. So a total of 3 plus 1 equation gives you a total of four unknowns. So the outshot of these, of course, is that people use these kind of simulations. And I remember reading of this one guy, I forget his name now, in Stanford, either in fluid mechanics or mathematics, who won an Oscar for rendering. So this is how you do movie special effects. You want to be able to represent a curtain fluttering in Toy Story or something. And so you do the fluid dynamics analysis of having a curtain move and solve the equations. and then you render or you drape a curtain on it, and it moves in some kind of lifelike manner, just as you're seeing here. So this isn't a pure numerical model. A numerical model would give you velocities in X, Y, and Z as a result of the simulation, and a pressure which you wouldn't see. But if you want to be able to render something on that which looks like waves hitting a lighthouse, you have to be able to paint something on top of those velocities and those free surfaces on the tops of the waves as you do it. So maybe that's an outshot for the kinds of things that we're talking about. A lot more sophisticated, of course, than what we're dealing with right now. Just make sure that these are off. Yeah, fine. I'll get rid of those. So back to the mundane realities of our life, I guess, perhaps. And that is to talk about what we are interested in. So our task is perhaps a little simpler than that in terms of what we want to figure out. Today, all I want to do is a recap on what we talked about last time. I plan to do maybe 3 examples, which are in these notes. And maybe we'll talk about porous medium flows if we get there. I don't think we'll talk about either of these. Flow between plates and flow in a pipe is relevant to us, because if you think about that first in-grain video of the porous media flows, you could think of the pathway of those individual blobs as being flow within a pipe. So we could use that to be able to represent porous media flows. And of course we might be interested in flow in pipes for well bores and piping systems in different systems. So what did we do last time? We talked about 2 expressions. The first one we said we'd used the most was Bernoulli, which we now have a pump head term, which is equal to, well, it's written down here, but the most usual representation of that is a head, which is length, is related to power, which is in watts, needed for a pump, multiplied by the mass flow rate times gravity. This equation here, I'm just repeating that. This is the way that I always remember it. Just this is a total work out of the system. And so this is HP, we said, is positive if it's a pump. So if energy is going into the system, it's positive. It's negative if it's a turbine. This is the upstream. So now we have, after week 8, we have to write upstream and downstream. We didn't care before because we didn't have losses. And so this is energy into the system. This is loss within the system. And you can imagine the losses being for 2 things. You can imagine what we'll look at. We don't need to worry about this now. We'll be worried about fluids going around bends. And in pipes, this is my attempt to draw a pipe. Whoops. So if we have velocity 1 and velocity 2, Bernoulli would tell us that velocity 2 equals, so long as the area 1 is equal to the area 2. So if the cross-section areas are the same, by definition, the velocities out of these are the same. However, let's assume that the areas are the same. However, if viscosity is not equal to 0, in other words, it's a viscous system, then V1 probably isn't is not equal to V2. In fact, V1 would be typically greater than V2. And the reason for that is that, well, there's a bit of a problem there because continuity requires that those have to be the same. And so I guess that's not, so they do still have to be the same. So I guess that's not true now I said it. So forget that. But my point is that the velocities would be reduced over the velocities for Bernoulli. So V1 Bernoulli would be greater than V1 mu not equal to 0. Yeah, that's better. you realize that if the cross-sectional areas are the same and it's steady state, de facto, they have to be the same velocities. And the point I was going to make is that these losses are due to what are called minor losses, which are given by an equation like this, which we'll talk about in pipe flows, which is a loss coefficient, which is some number KL, which is typically less than 1 and greater than 0, which operates on the velocity. And it just accounts for the fact that the water's happily going in the x direction, then all suddenly, rudely, it has to go in the minus z direction. So changes in velocity are changes in momentum, and they're changes in energy loss within the system. And so we need to be able to account for that in looking at energy losses minor. And we'll talk about energy losses major, which are flows, energy losses within the pipes due to the longitudinal flow. And they are something like a friction factor, a length to diameter ratio, and v squared over 2g. And so this would be a diameter of a pipe. This would be the length of the pipe. And all it's saying is that we can scale what these losses are, either as minor losses or major losses, if we know something about the system we're dealing with. And the fact is that they scale with the velocity head. This is a length, right? So this is a length, this is non-dimensional, and this is a length. Likewise, this has to be a length for Bernoulli. This is non-dimensional, this is a ratio of two lengths, and this is a length. So they're dimensionally homogeneous. So I didn't quite finish my thought. This has to be downstream. And this is always positive. A loss, we don't, if it's putting energy into the system, it's actually a pump, so it can't be. It's always a loss for the arguments we had about pulling a bag across a table. So that's one way of dealing with this. And I guess I won't repeat it, but I could draw it for you. I guess I could be even fancy. I could steal it because it was such a nice figure. I know it's cheating because I can do this quickly and you can do it less quickly with my lasso command. Doesn't, or perhaps I can't. Well, I can drag it, but I'm sure I can't drag it very well. Okay, I can't. Well, let's give up on that one. So I couldn't draw that. I mean, the basic idea of this, I think it's useful to repeat it because it does kind of explain exactly what's going on. And otherwise, we're just doing some, drawing some equations today, is that we talked about a system where we had, oh man, flowing from upstream to downstream with a pump in it. Point upstream, point downstream. I can draw a datum. So this is just to this exact point is, as you know, Z1 and Z2. They don't have to be the same height. It's just easier to draw them this way. This is the pressure head. P1 over gamma, P2 over gamma. If it's a pipe of constant diameter, then the velocities upstream have to equal the velocities downstream. And then we made the point that this extra term that we have on the upstream side and the extra term we have on the downstream side are just these individual terms. And so you could imagine that really this term H pump, you probably are putting it in right here. And so you're going across here, you're going up here, you're going across here, and then you're going down here. But I suppose what it would look like really is the pump goes in right at the pump, and then it goes in, the head loss is a head loss over the total length of this pump as it's flowing, actually over the whole thing. So it's easy enough just to think of it in the ways that I drew it. You're adding energy into the system. On the upstream side, you're taking it out at where it arrives. And so that explains exactly what these terms are. So that's our easiest way to think of this. This is the one that we'll use 90% of the time. I guess we made the case that the one that we might use 10% of the time gives us a different component, because this enthalpy term here, enthalpy per unit mass, I guess enthalpy over mass. So joules, kilojoules per kilogram, or joules per kilogram, is equal to the internal energy plus pressure divided by density of the fluid. And so we use that. So you see that now the pressure is included in this term. So this term includes pressure, velocity, and head. So it's kind of Bernoulli, but now it has this extra internal energy term. So it relates directly to what we started talking about last time. We had this nice Ever movie talking about geothermal energy. So geothermal fluids are hot. They have internal energy in the heat. And when you flash them to steam, they give up that energy in addition to the fluid pressure in terms of the phase transition. And so we can account for that energy in some way in the energy equation. This is mass flow rate, what we've called uppercase M dot before. And this is thermal energy, heat energy in. And this is work in. So this would be pumping, right? Physical work in would be pumping. Heat energy would be heating the fluid that's in the system, or adding heated fluid to the system. So that's it. So that's, in a nutshell, if you like, our equations. We used number 2 last time for one case with a turbine. Comes in at some enthalpy, goes out at some enthalpy. How much energy is taken out of the system in terms of work from that? Then we can do that as long as we know the mass flow rates, and we know the elevation was constant. We knew it had different velocities, which is coming in at a different velocity than going out. But of course, since it's steady state, the mass flow rate through the system has to be constant for steady state. And so if we know what that mass flow rate is, we can calculate how much energy comes out of the turbine, which is what we did last time. Okay. So what I propose to do is do 3 examples, one of which matches one of the examples we did last time a little bit, the third one, but just go through some examples. And we have plenty of time to do that. And so first one is pumping fluid from one tank to another. You're pumping it uphill, so you'd think that you'd be using some energy to be able to do that. You could write your velocities, I suppose, anywhere within the system. But let's go through the example. A pump transfers water from one large tank or one large reservoir to another. This is code, right? You know, this means that velocity V1 equals 0, large tank. Velocity V2 is equal to 0. So that's what this means. Difference in elevation is 100 feet. Well, I promised SI only, but this would be Z2 minus Z1, right? Z1, Z2. Because this is upstream, I guess, we have to realize that. This is downstream. If we're pumping from 1 to 2. Doesn't say that, but that's what we're doing. Frictional head loss in the piping is given by this term here. So we could write head loss is equal to this coefficient times average V squared over 2G. It's important to realize that this is an average velocity within the pipe. So V bar equals pipe velocity, because obviously V1 and V2 are 0, so the loss would be 0. So this is defined relative to a local velocity in the pipe where it's non-zero, where it says that, the average fluid velocity in the pipe, which should be, of course, V bar would just be equal to the volumetric flow rate divided by the cross-sectional area. Considered constant. The relation between the total head rise across the pump and the flow rate through the pump is given by this figure here, which we'll come to. And just while we're on this loss coefficient, you have a value for this which is equal to 20. I said it's typically between 0 and 1. For pipe fittings it usually is, but this is for the pump loss, I guess. And the pump equation for the head loss across is given by this. So this would be H sub P. This would be volumetric flow rate. And of course, the equation of this straight line is this equation here. Right? Head loss when the flow rate is equal to 0. This is equal to 0. Then HP is equal to 2 times 100. 200 feet of water. It's important to note that this is not a non-dimensional equation. It's equal to feet on the left-hand side, and it's equal to feet, cubic feet per second on the right-hand side. So I guess you could think of this being multiplied by a coefficient which would be in units of seconds per feet squared, if you wanted to, right? So in other words, if you had a coefficient in there which was A, the units of A would be seconds per feet squared, so that cubic feet per second times seconds per feet squared is equal to feet, which is equal to the left-hand side. Perhaps not worry about that. Probably not important for this example. But sometimes you have to be careful with your units. And I guess I digressed that when Q, of course, is equal to 2, if Q is equal to 2, then the pump head is equal to 0. So you recover these 2 points from this equation, but you also recover all points in between. It's just the equation of a straight line. And so what are we interested to solve for? What's the flow rate through the pipe? So I guess we want to know either V bar, or we want to know what Q is. They're related in some way, right? So we can work from Bernoulli. Do they use Bernoulli? They pretty much use it. So what do we know? P1 is atmospheric. P2 is atmospheric. If we take gauge pressure as the zeros, so this is 0, this is 0, this is 0, this is 0. We're making our life very easy. But we don't have zeros on the elevations, and we don't have zeros on the pump head, which we know here, and we don't have 0 on the head loss, which we have here. So that's our basic equation. So out of this one equation, we want to get velocity, average, and so we just have to figure it out. So if we take Bernoulli and figure out what terms we have left, then that's this equation here, number 1. Pump head is equal to Z2 minus Z1. Take this plus head loss. We have a pump head which is given by this, which we might not be able to use straight away. And we have a head loss, which is equivalent to this from here. Since the pump head is written in terms of a volumetric flow rate and the head loss is written in terms of a velocity, we need to link those two together. So I suppose we can do that by noting that velocity is equal to volumetric flow rate over area, and volumetric flow rate over area is equal to pi d squared upon 4. So uppercase D, we've got diameter of the pipe. Must have diameter of the pipe somewhere. I don't see it. It's here. Pi d squared upon 4, which allows us to be able to either write this equation in terms of Q or write this equation in terms of V. And so I guess in this case, the choice is to write HL in terms of Q, just by substituting V squared as Q squared. So in other words, we'd write this equation here. Oh. So if that's what happens. So if I do it as a line that has a little drawback, oh, it writes it as an arrow. Didn't do it that time. So this is this term here. And then we have HL equals a function of Q. We have HP is a function of Q. And therefore, if we substitute HL and HP back into this Bernoulli equation, we have this equation as a function of Q and a value of these two differentials. This is just 100 feet, right? So if I go down here, if you substitute this term for this and this term for this, and then you go through the algebra, then you end up with a quadratic term. Q squared because of this term, Q because of this term, and a constant because of Z2 minus Z1. So you end up with a quadratic equation. And quadratic equation would have two roots. You solve for the two roots. One is probably a negative flow rate. One is probably a positive flow rate. And you take the positive flow rate. We won't go through the mechanics of this, but you use the quadratic equation to solve it. So I think the mechanics are more important, obviously more complex than a exam question, but the basic way of doing it is to be able to realize that you need to solve Bernoulli equation. You know most of Bernoulli equation except for 4 terms. 2 of the terms are the elevation drop. 1 of the terms is the pump equation here. 1 of the terms is the head loss, which is given by the velocity of flow through the system, this term here. And so long as you can write it in terms of a single variable, which in this case could be velocity, or it could be Q, it could be either one, you could do either one. If you wanted to, of course, you could write this equation in terms of a velocity and then just use this straight. You'd get exactly the same result, except then you'd get a term which was in terms of V squared, V, and a constant, same constant. Okay? So that's it. So using Bernoulli again. Yeah.
So why did we put Q when we would like solve for HP and it was 200 minus 100 times Q? I'm confused where the Q comes from.
This one?
Yeah.
This comes just by multiplying out this, so 2 minus Q times 100 is equal to, it's just been multiplied out. I presume, right? Is that what it is? Yeah, I think that's what it is. Yeah, it's just that. It's just multiplying that head equation out so that you have that separately. And I guess, I suppose this 100 here is probably equal to 200 minus 100, right? You have 100 here. You're going to have 200 minus 100 Q instead of this. And so this 200 and this 100 together will conspire to give you this remaining 100, I guess. Right? So, yeah. All right. No problem. Okay. Questions? Okay. All right. Same deal. Yeah, we have time to do this. So the same kind of idea. So let's go through it step by step. Gasoline, lighter than water. So delta gasoline is equal to rho water times Sg. So it's 0.68 times the density of water, so 680 kilograms per cubic meter. It is in SI this time. Flows through the pump, goes through at a volumetric flow rate. Q is equal to 0.12 cubic meters per second. When I write this, is it super small for you? I can write larger if you need me. We've got a head loss here, which is equal to this. So this would be HL is equal to KL times V1 squared over 2G. This is 1. This is velocity V1. So it has to be one of the velocities. I guess the little wrinkle in this is that D1 is not the same as D2. So this is a smaller diameter. This is a bigger diameter. And so you have to classify this head loss in some way relative to one of the velocities. And the velocity V1 will not equal velocity V2. Because velocity 1 times A1 will equal velocity 2 times A2. Continuity, right? And so what we can do is we can always get velocity 1 will be equal to velocity 2 times the ratio of those two to be able to link them together. So when we write Bernoulli, this gets rid of one of the velocity terms. It looks like we have two unknowns, but they're linked in some way, so we can link them together. So what do we know about this system? What's it asking? It's saying if we have a 20 kilowatt pump in the system, what's the difference in pressures? So the difference in pressures would be P1 minus P2 equals the difference in pressures. And so I always write Bernoulli this way. They've written it differently here, but I just choose to write it this way because it's easier for me. We don't know what this pressure is. We don't know what this pressure is. We do know what V1 is. So I guess we know that V1 is equal to Q over A1. This is equal to 0.12. And we also know that V2 is equal to 0.12 cubic meters per second over A2. So I guess we know both V1 and V2. We know that Z1, if we write our datum here as Z equals 0, then we know this. And we also know that this is equal to 3 meters because of this. And I hate writing things like this because I never use this. This obviously is HP. And I like to write HP is equal to watts per density per volumetric flow rate per G, right? This term here is mass flow rate, what we've called m dot. So density times volumetric flow rate, kilograms per meter cubed per second is kilograms per second. So this is m dot times G. I just find it easier. And this is power. So if 20 kilowatts is power, so in the system. So I guess what have we done here? So now what we do is we take this equation, even though I'm running out of space. We know that this is, did I write it somewhere? HL is equal to this. And we multiply both sides by rho G. If we multiply by rho G, we get rid of this. We end up with this equation here. So if we multiply this whole equation by rho G, we get rid of the rho G that's under the pressures. We get rid of the 2G with a rho outside on the velocity term. We add a G and a rho to the Z, and we do something with this. This is the modified shaft work per unit mass flow rate. This is just work per unit mass flow rate. Small w is work per unit mass flow rate. Big W is power per unit mass flow rate, power total. And so this is system. And so we have these terms, so we just need to figure out exactly, we know what the velocity 1 is, because it's the volumetric flow rate divided by the cross-sectional area. We have a diameter. So we can get volumetric 1 or volumetric 2. Easier to get, well, it's not easier, you can do either one. Volumetric flow rate, which is constant. Area of flow of cross V2 is this, the diameter, pi d squared upon 4. It gives us a value of V2. We can link V1 to V2 from what we did here, just continuity, right? So V1 is equal to V2 multiplied by the ratio of the cross-sectional areas. It's a bit easier because the cross-sectional areas are just the ratio of the diameters, because pi and 4 cancel out top and bottom. So that's a bit easier. And so this is equal to V1. So we have V1 and V2. We have the difference between Z2 and Z3 is just 3 meters. We know which planet we're on. We know what the, this is the loss. So this has been, this term here is HL multiplied by G is out. I'm not sure how the loss compares. Let's see how they do it at the bottom. So anyway, so W shaft is just this shaft work here that we defined, divided through by the mass flow rate. Right, so I guess can we do that up here? We have it here. It's these equations here. I hate using this. So W rho QG is equal to little w G. And so I'm not sure what they were doing. If you want big W, then you can multiply both sides by rho Q. Is that what they did? I can't remember. Problem comes from following someone else's working in this. This is shaft net in. So this is, I guess they're already doing it as so this is being, they're multiplying both by G. So let me go back, let me get rid of this. they're doing this. So this is it. W dot rho Q is equal to lowercase w dot. That's all. Which is kind of complicated. I wouldn't have done it that way, but that's exactly what they're doing here. And it's to get this term, which is here. And so we have this because we know what the volumetric flow rate is. We know what the density of the fluid is. The density is just the density of water times 0.68. And so we know what the value of this is because we know that this is 20 times 10 to the 3 watts. This term here, which is 20 times 10 to the 3 joules per second, which is Newton meters per second, which is a watt. So that's this term which is going in here. And we know that the loss is defined in terms of this term here, which is a velocity that we have multiplied by 0.3. And so I guess this is the final equation. This is what we want. This is the density of water times Sg, which is rho. On this, can I keep both equations on? So this term here is this. This is equal to V1 squared minus V2 squared over 2. This is gravity. This is the head difference between upstream and downstream. And multiplied by conversion. This is the shaft work, which comes out of this equation here, which is this. This is 20 kilowatts, which is this term. And the final remaining term is the loss, which is it. So more complicated than it needs to be. I think switching it to this form is not so clear to me as using it always in this form. I'd have used it just in terms of these length values and this length value here, just because it gets complicated too soon. And then converting it somewhere down the road just to get the heads, which are P1 minus P2 over unit weight. You'd end up with a term that would be that, and then you just multiply that by rho g. So I think that would be easier to do. But that's not the hand that we've been dealt in this particular one. Okay? Questions? Yes?
Where did the equation for the shaft work that you have circled, where did that come from?
This one here or further up?
That one there.
This, yeah, okay. So this, I can do it here. So we started off with Bernoulli, which has been in terms like P1 over gamma, which is this, and would also have terms like HP. So our terms then would look like P1 over gamma plus HP, which is power, divided by density times flow rate times G. That's the equation for HP. And so what they have done here to get from this equation to this equation is that we've multiplied both sides by this unit weight, which is multiply this by rho g. This is unit weight, which is the same as this. And we've multiplied this by rho g. And so as a result of that, we've dropped this term here. We've dropped this term here. We've dropped this term here. And we've dropped this term here. And And so, yes. So we've done that. And so they've reported this then. I guess no, they haven't, right? So they've taken the Q, rho is still outside. So we've done that. They've kept the rho which is outside the bracket. And so this term has gone to be W dot over rho Q. And this is equal to, I think it's equal to what we've called lowercase w. Make sense? I think that's exactly what they've done. So we've started off with this term here has been HP. We've replaced HP by watts per mass flow rate over G. We've multiplied both sides of this equation by rho G, rho G, and so that's got rid of this G top and bottom. This hasn't been a term here because the rho has been outside. And so now this term, shaft work per unit mass, is equal to total work per unit mass divided by mass flow rate. So I think that's this here. So W dot is equal to this term here. Yes? Kind of. So, well, it's up to me. If I was doing this example, I would do it this way. So let's go. I would do P1 over gamma plus Z1 plus V1 squared over 2G plus HP equals P2 over gamma plus Z2 plus V2 squared over 2G plus HL. HL is equal to 0, was it 0.3 or is it KL? Remember? 0.3. So this is equal to 0.3 times V1 squared over 2G. This is equal to uppercase W times density times volumetric flow rate times G. And I would rearrange this in terms of taking this term to the left-hand side and taking everything else to the right-hand side. So I'd end up with P1 over unit weight minus P2 over unit weight is equal to Z2 minus Z1 plus V2 squared minus V1 squared over 2G plus HL minus W dot rho QG. And then I would change that to being maybe P1 minus P2, which is what we want, is equal to, let's see if I can be clever and do it this way this time. This whole expression here doesn't let me duplicate it. Can't do it. So let me write it. Z2 minus Z1 plus V2 squared minus V1 squared over 2G plus HL minus W dot rho QG multiplied by the density of water times SG times gravity. That's what unit weight is. Okay? So I have something in the way that I want it, but now I have to figure out what these individual terms are. So the individual terms are, this is 3 meters. This is equal to Q divided by area 1 squared. This is equal to Q divided by area 2 squared. This is equal to 0.3 times V1 squared over 2G. And V1 squared, of course, is a function of Q. And this is equal to 20 times 10 to the 3. Density is equal to the density of water times specific gravity. Flow rate is 0.12 cubic meters a second, and G we know. So this conversion between lowercase w and uppercase w, I think, is kind of a red herring. You avoid that if you just use this term. And I guess this is this term here. Does that solve it better? That's a bit clearer, perhaps. That's how I would do it. Lots of hands up.
The 0.3, the KL term, where did you get that from?
I think it was, or perhaps it was the previous one. Was it KL? Yeah, it was KL. 20 was here. It's 0.3 in this one. Here.
Okay.
Given.
What is that?
It's just a number. It's a non-dimensional number. It says that if we believe that the losses within our system are conditioned by this term here, it says that the head loss we can classify as being equivalent to something like this. It scales with the velocity flow rate in the pipe divided by 2G. We know that the units of this, because of Bernoulli, have to be units of meters. The units of this have to be units of meters. And so this is just a scaling constant.
It's a constant loss.
Yeah.
basically.
Yeah, it's a loss. If it's a big number, it's a big loss. If it's 0, it's no loss.
Okay. And the lowercase w, is that work over unit mass flow rate?
Yes.
Okay. Thank you.
Abigail?
What was the big W again?
Big W is power. So this is important. Head power into the system is given by watts, which is power, per mass rate times G, which is the same as power per volumetric flow rate times density, which is mass flow rate, times G. And to me, that's the easiest way to use it, which are in units of watts per watt. Watts per meters cubed per second per kilograms per meter cubed per gravity. So these mass flow rates cross out. So this term here is kilograms per second, which is a mass flow rate, times G. And I never use lowercase w, but it's shaft work per unit mass flow rate. So if this is 1, then this is the work per unit mass flow rate.